So welcome back, Level 2 NCEA Physicists. Today looking at a new internal, atomic and nuclear physics, and beginning with the ideas around the models for the atom. Okay, so the early models of the atom were based around two Greek philosophers about 2,000 years ago. The first one being the Greek philosopher Democritus, who basically said matter was made up of small particles, and he named these particles atomos, meaning indivisible. Okay, and that was his model right there. And the competing ideas were from another Greek philosopher, which is a little bit more famous, or who was a little bit more famous, named Aristotle, who said you couldn't actually divide matter into particles. Okay, it was all around their qualia, their qualities, and he said once you start dividing things, you'll end up with matter being divided into four elements: fire, earth, water, and air. So basically, if a substance had particular qualities, then they had particular elements, all bound together by a fifth element called ether. And that model stuck around for about 2,000 years, until the 1820s, when a British chemist named John Dalton reintroduced the idea of Democritus's atom and had several statements based around experimental evidence. Okay, and his ideas were that all atoms of a given element are going to be identical. So every atom of gold will be the same as every other atom of gold. That atoms of a given element are going to be different from atoms of other elements. Okay, so oxygen atoms are different in terms of mass and size to carbon atoms, for example. And that atoms from one element will combine with other elements to form something called compounds. Okay, so water is made of a hydrogen or two hydrogen atoms and one oxygen atom, so they're in fixed ratios. And that the atoms cannot be created or divided into smaller particles, and they cannot be destroyed by chemical processes. They just change their positions in compounds. Okay, they're essentially indivisible, just as Democritus said, and that chemical reactions change the way that atoms are grouped together. That's what Dalton came up with in the 1820s. Moving along to the turn of the 20th century, J.J. Thomson discovered the electron through his discovery of cathode rays and using cathode ray tubes, and went on to propose the plum pudding model. So essentially the plum pudding model is that you have this amorphous blob of uniform positive charge, and inside that positive charge is going to be small little electrons, just like a plum in a plum pudding model, hence the name. Okay, and then one of Thomson's PhD students, named Ernest Rutherford, about 10 years later, sent alpha particles, which are basically helium nuclei, which we'll look at later as well, which are quite slow moving atomic particles, through very thin gold foil. Okay, so because the reason why he chose gold, it's quite easy to form into foils and make it very thin, so several atoms thick. So what he predicted, that the alpha particles, if the plum pudding model was correct, would pass straight through. However, that's not what he saw. Okay, so what he actually saw, that although he thought with the plum pudding model that the alpha particles will travel straight through and not deflect much, what he saw was quite a bit of deflection. Okay, way more scattering than what he expected. Okay, so then he had to propose a new model of the atom, and that's Rutherford's model of the atom. And the reason why is that the reason why you see these deflections is that basically most of the atom's empty space, but inside the center of the gold atom is this dense positive charge, which he coined the nucleus. Okay, so when the positive alpha particles hit this positive nucleus, they basically bounce back, or they were deflected because obviously like charges repel. Okay, so that was essentially Rutherford's model of the atom. So Rutherford's model of the atom basically stated that because most of the alpha particles were deflected less than 5 degrees, there was a really small nucleus, positive nucleus inside the atom. Some of the positive particles were deflected or repelled, so that said it was positive. Okay, it wasn't negative because there was that repulsion because the positive charge of the alpha particle and the positive charge of the nucleus were occurring through repulsion. And because a few of the alpha particles bounced back, it meant that the nucleus was very dense, but also very small. So dense, massive, but very small. Okay, so that's basically the Rutherford's model, and that's what you have to critique in your internal with that of Thomson's.